In the summer of 2018, a structural engineer working at the Megiddo excavation site in northern Israel pressed the tip of a Schmidt rebound hammer against the inner face of a limestone ashlar block set into the remains of a casemate wall dating to the Iron Age .ia period, approximately the 10th century before the Common Era. The Schmidt hammer is a simple instrument. It fires a spring-loaded plunger against a surface and measures the rebound. The higher the rebound number, the harder the surface. She had been testing blocks throughout the excavation for 3 days, building a hardness profile of the surviving masonry to assess structural condition. The readings on exterior-facing blocks were consistent with expectations. Meliki limestone, the dominant building stone of ancient Israelite construction across the Levant, weathers predictably over millennia. Surface hardness decreases as carbonation, thermal cycling, and moisture infiltration slowly degrade the crystalline structure of the stone. A freshly quarried block of Meliki limestone produces a Schmidt rebound number in the range of 38 to 44. A block exposed to the elements for 300 years should produce a reading in the low 20s, possibly the mid-teens if water infiltration has been significant. The exterior blocks at Megiddo were reading 19 to 24, exactly as predicted. Then she moved the hammer to the inner face of a block at a mortar joint interface, where the limestone met the lime mortar that had been packed between the courses when the wall was originally constructed. The sound was wrong. The strike produced a sharp, high-frequency ring, the acoustic signature of dense, hard material, not the dull thud of weathered stone that she had been hearing for 3 days. The rebound number was 46. She checked the instrument. She recalibrated the spring mechanism. She struck the surface again. The reading was 47. The surface of this block, at the precise point where it met the ancient mortar joint, was harder than freshly quarried Meliki limestone. It was harder than it had been the day it was cut from the earth, 300 years ago. The following week, laboratory petrographic analysis of a mortar sample extracted from the adjacent joint confirmed what the Schmidt hammer had measured. The lime mortar, a mixture of calcined limestone paste and locally sourced aggregate placed in the joint sometime during the 10th century BCE, had been undergoing continuous carbonation for 3,000 years. Atmospheric carbon dioxide, penetrating the wall through microporosity at rates measured in fractions of a millimeter per century, had been reacting with the calcium hydroxide in the mortar to produce calcium carbonate crystals. Those crystals had been depositing at the stone-mortar interface, filling the microscopic gap between the two materials, bonding them at the crystalline level, and in the process, increasing the surface hardness of the adjacent limestone beyond its original quarried value. The mortar joint was not deteriorating. It was still curing. It had been curing for 300 years, and the hardness curve, plotted against the carbonation depth data, was still pointing upward. The modern equivalent of that mortar joint, a Portland cement mortar joint laid to current ASTM standards, has a designed service life of 25 to 40 years before repointing is required. The Megiddo joint has been in continuous structural service for approximately 3,000 years and shows no measurable indication of approaching the end of its functional life. That Schmidt hammer reading, 47 on a surface that should have read 22, is the number that frames everything that follows. It is not an anomaly. It is not an artifact of unusual site conditions. It is the predictable, chemically inevitable result of a specific construction material doing exactly what that material does when it is formulated correctly and placed in a joint geometry that allows atmospheric carbon dioxide to reach the unreacted calcium hydroxide in the mortar core. The chemistry is undergraduate level inorganic reaction kinetics. The structural implication is not undergraduate level anything. It means the Israelite builders who constructed the Megiddo casemate wall used a jointing material that does not degrade toward failure. It strengthens toward an asymptotic maximum that the material has not yet reached after 3 millennia. Every modern mortar and cement formulation in current commercial use degrades from the moment of initial set. The question of what that comparison means for the construction progress narrative over the past 300 years is not addressed by the Schmidt hammer, but the Schmidt hammer has provided the data point around which that question must now be organized. The 7 techniques documented in the following structural analysis are not separate innovations. They are 7 expressions of a single construction philosophy that produce structures across the ancient Israelite Levant, at Megiddo, Hazer, Jerusalem, Lachish, Beersheba, and Gezer, whose structural performance after 300 years exceeds the designed service life of every modern substitute that replaced them. The philosophy can be stated as a single engineering principle. Use locally sourced natural materials, process them at low temperature through methods that require time rather than energy, and allow the resulting construction to reach its final structural state gradually through ongoing chemical and mechanical processes driven by the environment the structure occupies. Lime mortar that carbonates over centuries. Dry-laid stone joints that polish themselves under sustained compressive load. hydraulic plasters whose pozzolanic reactions continue to densify the matrix for decades, cedar timber courses whose slow seasoning in place reduces their stiffness and increases seismic energy absorption. Every material in the system continues to improve after installation. The modern materials that replaced each of these, Portland cement, steel reinforcement, synthetic waterproofing membranes, rigid concrete connections, share a different trajectory. They are strongest on the day they are installed and degrade from that point forward toward a designed failure state. Reinforced concrete, 50-year design life per American Concrete Institute standards. Modern mortar joints, 25 to 40 years. Modern timber framing, 20 to 30 years. Synthetic waterproofing membranes, 10 to 20 years. Every one of these numbers represents a designed replacement cycle. Every replacement cycle generates revenue. The ancient techniques have no replacement cycle. They have no endpoint that has been reached or projected. The Megiddo casemate wall has been standing for 3 or 0 years, and the mortar is still getting harder. The concrete wall that a contractor would build on the adjacent lot has a 50-year design life and a degradation curve that begins the day the forms are stripped. Both are fully explained by structural mechanics and materials science. Neither is mysterious. The comparison between them is the kind of data that a $10 trillion global construction industry has no economic incentive to publicize. The casemate wall system documented at Megiddo, Hazer, Beersheba, and Gezer is the first of the 7 techniques, and it is the one that structural engineers who encounter it find most difficult to reconcile with the assumption that wall construction has improved since the Iron Age. The Israelite casemate wall is not a solid wall, it is a hollow wall. 2 parallel walls of dressed ashlar limestone, typically 5 to 1, 6 meters apart, connected at regular intervals of 2 to 3 meters by perpendicular cross walls of identical construction, creating a series of enclosed rectangular chambers running the length of the wall. In cross-section at an excavation site, the system is immediately legible. The 2 outer walls are precisely dressed ashlar, the cross walls connecting them at mathematically regular intervals, the chambers between them filled with earth and rubble that has compacted over millennia into a mass now structurally integral with the wall rather than merely contained by it. A solid limestone wall, 3 meters wide, the total width of a typical casemate wall, at 4 meters height, weighs approximately 200 kilograms per linear meter. The casemate wall of identical external dimensions weighs approximately 300 kilograms per linear meter, a 40% reduction in stone mass. The lateral load resistance, however, is not reduced by 40%. In the unloaded chamber condition, it is reduced by less than 15%. In the rubble-filled defensive configuration, the lateral load resistance meets or exceeds the solid wall because the compacted fill between cross walls acts as a composite shear panel, transferring load through friction and passive earth pressure rather than through the tensile strength of stone alone. The cross walls function as shear connectors in a composite system. The filled chambers function as confined granular shear panels. The result is 40% less quarried stone, equivalent or superior lateral resistance, thermal mass performance, equivalent to a solid wall twice its thickness because the air gaps and fill material provide insulation, and modular repair capability because each chamber is a structurally independent module. Damage to one chamber can be repaired without compromising adjacent sections. Modern structural topology optimization software, the algorithmic process by which engineers determine the minimum material geometry satisfying given structural loads, produces wall geometries for lateral load resistance recognizably similar to the casemate cross-section. 2 outer skins connected by periodic web members with infill panels. The algorithm arrives at this geometry because it is optimal for the load case. The Israelite builders arrived at the same geometry 300 years before the algorithm existed. The modern replacement is the solid reinforced concrete perimeter wall. It is heavier. It has no modular repair capability. Its reinforcing steel begins corroding the moment chloride ions penetrate the concrete cover, a process that in coastal or arid salt-rich environments like the Levant takes 15 to 25 years to initiate. The casemate wall has no steel to corrode. It has no material that degrades in its operating environment. The replacement was not driven by structural performance. It was driven by construction speed. The second technique is subtler and easier to miss because it operates at a scale invisible without precision measurement. At multiple Israelite sites, most notably Hazer and Megiddo, large Proto-Aeolian capitals crowning monumental pillars are seated on their supporting columns, not on flat bearing surfaces, but on gently convex curved surfaces. A deviation of 3 to 8 millimeters from flat across the bearing diameter. Easy to interpret as imprecision in stone dressing. Structural analysis tells a different story. When a capital sits on a flat surface and lateral force is applied, wind, earthquake, any non-vertical load, the force transmits directly through the flat joint as compression on one side and tension on the other. Stone is strong in compression. catastrophically weak in tension. The flat joint under lateral loading produces a tensile stress concentration at the upwind bearing edge that initiates fracture. The column fails suddenly and completely. This is the documented brittle failure mode of stone columns in seismic events at every major earthquake-affected archaeological site in the Mediterranean. The convex surface changes the mechanics entirely. Under lateral force, the capital does not transmit the full load. It rocks. The convex surface acts as a pivot. The capital rotates in micro-rotation, fractions of a degree, lifting off one side and compressing the other. The lateral force converts from direct transmission into a rocking motion that dissipates energy through the gravitational restoring force of the capital's own weight. The capital rocks, absorbs the lateral energy, returns to center. No tensile stress develops in the column shaft. No fracture initiates. In modern structural terminology, this is a rocking isolation joint, the same mechanical principle used in base isolation systems, costing $500 to $2,000 per square meter of building footprint. The Proto-Aeolian capital achieves it with 3 to 8 millimeters of bearing curvature at zero additional material cost. The seismic record confirms columns with convex seated capitals show dramatically lower failure rates across the seismically active Levant than flat-seated equivalents at contemporary sites. The modern replacement is the rigid, grouted connection, stiffer, stronger in pure vertical compression, catastrophically vulnerable to the lateral loading that earthquakes produce. It was adopted because it is faster to construct and simpler to analyze using linear elastic methods. The rocking joint requires nonlinear dynamic analysis, methods unavailable until the 1990s. The Israelite builders did not have nonlinear dynamic analysis. They had 3 to 8 millimeters of curvature and 0 years of seismic performance data. The third technique operates at the chemical level. Throughout the Negev and Judean highlands, Israelite cisterns are lined not with simple lime plaster, but with a specific formulation. Lime plaster mixed with crushed fired pottery, shamat, and fired silica aggregate. When calcium hydroxide contacts the amorphous silica in fired ceramic, it undergoes a pozzolanic reaction producing calcium silicate hydrate crystals, the same compound responsible for Portland cement's compressive strength, but through a slower, lower temperature process that does not require 450 degrees Celsius kiln temperatures. The practical consequence, Portland cement also produces calcium hydroxide as a hydration byproduct, and that calcium hydroxide is vulnerable to sulfate attack. In the alkaline, sulfate-rich groundwater typical of Negev and Judean limestone geology, sulfate ions react with Portland cement's calcium hydroxide to produce expansive ettringite crystals that crack the cement matrix from within. Modern Portland cement installations in these environments require replacement every 15 to 30 years. The Israelite formulation is chemically stable because the pozzolanic reaction consumes the calcium hydroxide rather than leaving it vulnerable. No free calcium hydroxide remains for sulfate attack, and the reaction continues. Core samples from cistern linings in continuous water contact for 3 zero-zern years show pozzolanic products still forming at the plaster-water interface. The lining is still densifying, still reducing in porosity. The surface of a functioning 3 or 0-year-old cistern lining is cream white at the exposed face, shading to gray-green where moisture has been in continuous contact, smoother than it should be because the ongoing pozzolanic reaction has filled the surface micropores that were present at application. Place a core sample from a Portland cement cistern lining installed in the Negev in 1987 beside one from an Israelite hydraulic lime lining at the same site, dated to the 8th century BCE. The modern sample, after 30 years, sulfate-induced microcracking, visible to the naked eye, ettringite crystal growth at aggregate paste interfaces, permeability increased by a factor of 12 from its initial value. The ancient sample after 800 years, continued pozzolanic densification, no sulfate damage, no visible cracking, permeability lower than the modern sample's initial value, lower than it was when new. One of these materials is still being manufactured. One is still performing. They are not the same one. Portland cement production. 4. 1 billion metric tons per year. Hydraulic lime plaster, approximately 5 million. Portland cement sets in hours. Hydraulic lime requires weeks. The economics are not close. The performance comparison is not close either. They point in opposite directions. The industry follows the economics. The structures follow the materials science. The complete structural analysis summary, all 7 techniques, performance data, peer-reviewed references, documented replacement decisions, is in the pinned comment for anyone who wants the full technical record. The 4th technique concerns the lowest stones in a building and a construction decision that modern engineers recognize as structurally correct but economically impractical. At the Temple Mount platform in Jerusalem and at multiple Israelite administrative sites, the lowest courses of ashlar masonry, transferring the full building weight into the ground, are laid without mortar. Dry laid, block against block at bearing surface tolerances under 2 millimeters across the full contact face. The structural rationale addresses masonry's most persistent failure mode. Differential settlement. Uniform settlement loads masonry in pure compression. Acceptable. Differential settlement produces bending, and mortar joints become failure points because mortar is orders of magnitude weaker in tension than stone. Cracks open at the joints, water infiltrates, freeze-thaw cycling widens them. The wall deteriorates from the foundation upward. This is the most common structural distress pattern in aging masonry buildings worldwide. Dry-laid foundations eliminate this entirely. Under differential settlement, blocks microslide rather than crack, redistributing compressive load without tensile stress. The field evidence. Dry-laid Israelite foundations show no settlement cracking after 3, 0 years in seismically active terrain with expansive clay soils, conditions producing differential settlement in virtually every modern building in the region. The joint surfaces, examined under magnification, show contact creep, slow pressure-driven deformation producing surfaces that have microscopically conformed to each other over millennia. A contact patina is visible as a mirror smooth band at the bearing interface. 3 0 years of sustained compression polishing stone crystals to a surface finish no modern process replicates because no modern process applies load for 3 0 continuous years. The joint is tighter now than when it was laid. A feeler gauge cannot enter it. The modern replacement. Mortared courses on concrete footings, faster by orders of magnitude. The 2 millimeter tolerance achieved with copper and iron hand tools in the Iron Age is achievable today only with diamond-tipped CNC stone cutting equipment. The fifth technique is documented in 1 Kings 6:36. 3 courses of dressed stone and 1 course of trimmed cedar beams, repeating through the wall height of Solomon's temple, for centuries read as architectural description of decorative construction. Structural engineers at the Technion analyzed it as a seismic specification. The mechanism is direct. Cedar is approximately 100 times less rigid than limestone perpendicular to the grain. When a cedar course is placed between limestone courses and seismic waves travel upward through the wall, the cedar deforms laterally, absorbing energy through wood fiber, microdeformation, and timberstone interface friction. The lateral acceleration transmitted above the timber course is reduced by 15 to 40%, depending on earthquake frequency content. Multiple timber courses at regular intervals produce cumulative isolation. Each successive course filters more seismic energy so that upper wall portions experience dramatically reduced forces. This is the principle in modern base isolation systems, costing $500 to $2.00 per square meter. The cedar course achieves comparable performance at 0 additional cost as an inherent byproduct of the alternating construction pattern. Over time, the timber seasons slowly in place, decreasing moisture content reduces the modulus of elasticity, improving energy absorption capacity. The technique was not replaced by a better seismic isolation method within masonry. The entire wall system was replaced by rigid, reinforced concrete that transmits full seismic forces and requires either expensive base isolation or conservative overdesign. Within masonry construction, the cedar course remains the most cost-effective seismic isolation technique ever documented. Filed away in the literature as historical curiosity, while unreinforced masonry continues worldwide, and seismic damage to it remains the largest source of earthquake casualties globally. The sixth technique concerns hydraulic precision that is difficult to comprehend without standing beside the measurement equipment. Rock-cut water channels at Beersheba, Megiddo, Gibeon, and at Jerusalem maintain gravity flow gradients of 0, 0.5 to 0, 15% across distances of 50 to 500 meters, a 0, 1% gradient, meaning a drop of 1 millimeter per meter. Modern laser surveys show these gradients maintained to tolerances of plus or minus 3 millimeters over 100-meter spans. Not rough approximation. Precision hydraulic engineering. The gradient must be steep enough to maintain flow velocity, preventing sediment deposition, and gentle enough to prevent erosive velocities degrading the channel. A narrow window that the Israelite engineers hit and held through solid limestone with copper and iron tools, without any surveying instrument identified in the archaeological record capable of maintaining millimeter tolerances over those distances. The inferred technique, small reservoir basins at regular intervals along the planned route, each filled with water as a self-leveling datum. The overflow height from one basin establishes the entrance height of the next channel section. Each section is independently referenced. Precision accumulates rather than degrading because error does not compound across sections. A gravity flow channel meeting modern hydraulic specifications, built with tools a modern engineer would consider incapable of the demonstrated precision. The modern equivalent, laser-guided excavation with GPS base stations, identical tolerances at roughly 100 times the cost per meter. The seventh technique is the one structural engineers find most compelling because it is not a single element, but an integration whose combined performance exceeds its parts. At Iron Age domestic and administrative sites, building foundation, courtyard drainage, and household cistern are not three systems. They are one. Roof runoff channels to the courtyard, graded to a settling basin at its lowest point. Clarified water enters the cistern through a filtered inlet. The cistern is cut into bedrock directly beneath the building's center of mass and sealed with the hydraulic lime plaster described earlier. It simultaneously serves four roles. Water storage. Foundation ballast. When full, its mass loads the building center, resisting the differential settlement patterns most common on expansive clay soils. Thermal mass, water's high specific heat capacity, moderates interior temperature, absorbing heat by day and releasing it at night. And structural infill, eliminating the vulnerability of a subsurface void beneath the building's structural center. No element can be removed without degrading all others. The courtyard gradient feeds the settling basin, which feeds the cistern, which stabilizes the foundation, which moderates temperature, sealed by plaster, whose pozzolanic reaction continues improving for decades. Modern construction separates each function. Foundation, water storage, drainage, climate control. Separate cost with no integration benefit. When any independent system fails, it creates conditions the others were not designed for. Drainage failure floods the foundation. Settlement cracks the waterline. Failure cascades across boundaries that exist only because separate engineering disciplines designed them in isolation. The Israelite system has no such cascading failure mode. It fails only when the environment fails to provide rain. In 0 years, the Levantine rainfall pattern has not changed sufficiently to exceed its capacity. What the seven techniques share is now visible as a single structural property that can be stated precisely and measured against the property of the modern systems that replaced them. Everyone produces a structural element or system whose performance improves after installation. The lime mortar continues to carbonate, growing harder. The dry laid joints settle tighter under sustained compressive load. The hydraulic cistern lining continues to densify through pozzolanic reaction. The cedar courses season to lower stiffness and better energy absorption. The rock-cut water channel gradient, once cut, requires no maintenance. Limestone does not erode at the low flow velocities produced, and the precision surface is as accurate now as the day it was cut. The casement chambers compact as fill settles against cross walls, increasing composite shear stiffness. The integrated cistern foundation system reaches maximum structural efficiency when the cistern is full, immediately after the rainy season, precisely when expansive clay soils are most active, precisely when the building most needs ballast. Every technique operates on a timeline beyond the builder's lifetimes. Everyone was designed, as evidenced by consistency across multiple sites, centuries, and building types, to produce structures whose structural capacity at year 3,000 exceeds capacity at year 1. Modern construction is designed to a different standard. Not will this be stronger in 3,000 years, but will this maintain minimum acceptable performance for 50 years before the economic value of the building is exceeded by the economic value of the land as a development site. The 50-year service life is not an engineering limitation. Modern engineers can design for 3,000 years. The materials science is understood. The limitation is economic. A 3,000-year structure generates one cycle of construction revenue and no subsequent revenue. A 50-year structure generates 60 cycles of demolition, redesign, and reconstruction over the same period. The construction industry's economic incentives align with replacement, not permanence. The Israelite builders operated where material costs were so high relative to labor that permanence was cheaper than replacement. The economic context changed. The engineering did not improve. The structures from the changed economics are being replaced on 50-year cycles. The structures from the original economics are being measured by engineers who keep rechecking their instruments because the numbers should not be possible. But the numbers are correct. The Megiddo casemate wall mortar joint has a surface hardness of 47 on the Schmidt rebound scale. The freshly quarried limestone it was laid against had a hardness of 38 to 44. The mortar has made the stone harder than the day it came from the earth. That is calcium carbonate crystal deposition at the stone mortar interface, driven by 3,000 years of atmospheric carbonation. Basic chemistry, fully explained. And the fact that it is fully explained is precisely what makes it uncomfortable for an industry whose business model depends on structures that do not do what this joint is doing. The Schmidt hammer measures surface hardness. It does not have opinions about business models. It measured 47 on a surface that has been in structural service since before Rome was founded, before the Parthenon was designed, before concrete was invented, and before any engineer alive was born. That wall will, by every measurable indication, still be standing when every concrete structure currently under construction has completed its design life, been demolished, and been replaced by another structure with another 50-year expiration date. That is not an opinion. That is a hardness reading, a carbonation rate curve, and a service life projection that the data supports and the industry does not discuss. The wall does not require the industry's discussion. It requires nothing. It is still curing.